We're okay? Okay. Okay, good morning, everybody. Apologies for the delay. The previous presentation that was here left a little bit late, so we were a little bit late in starting. It's a great pleasure and an honor to introduce today's speaker of the HEOS Distinguished Lecture, Professor Petros Ioannou from the University of Southern California. A lot of you already know Petros, so I'm not going to say too much. He's one of the most well-known people in the systems and controls area. He has contributed in many fields, especially in adaptive control and in the transportation area. And he also contributed towards the initiation of the engineering school at the University of Cyprus back in the before 2000, so the engineering school started in 2001, but before that there was a lot, there was some people that contributed towards convincing the government to start the engineering school. So he has many contributions. I'm just going to, he has received many awards. I'm not going to list all of them, but I just wanted to mention a few that are very important. He won the Axel B. Outstanding Paper Award from the IEEE Control Systems Society. He won the IEEE International Intelligent Transportation Systems Society Outstanding Application Award, as well as the IEEE Transportation Technologies Field Award, which is the top award of the Intelligent Transportation Society. But more, the kind of the top award that he was actually received this year in 2022, he was indicted to the National Academy of Engineering, which maybe some of you already know. It's one of the top honors for academics in the United States. So we are very proud to have Petros at the University of Cyprus today, and as well as at the HEOS Center of Excellence. And the other thing I didn't mention is that he's also a visiting professor at the University of Cyprus, and specifically with the HEOS Center of Excellence. So he's a very important part of what's going on here as well. So today's presentation is entitled Rejection of Vibrations with Unknown Frequencies Using Robust and Adaptive Feedback.
Good morning, everyone. Thank you, Marius. One important information that Marius didn't tell you is that he used to be my PhD student. And in fact,
we don't know that.
He's the best. He's proved himself to be the best, or one of the, to be diplomatic, one of the best PhD students in terms of academic excellence and success. What he did with HEOS is really amazing. If I had to predict, I would never, I could only dream it, not predict it. But when it happened, it's not surprising. So Mario was always moving, very enthusiastic about things, research, and so on. He wanted to do a lot of things. So anyway, thank you, Marius, and thank you all for coming to the talk. I'm glad to be at HEOS. I came here before the mask period 2 years ago. And, I had a lot of topics to choose from, but I chose something that Marius also liked, and more of a controls problem. And of course, it has a lot of math and complications, but I tried to make it a little bit simple. So at least you understand something, okay? If not a lot. Does it go? Okay, so this is a list of topics I'm going to talk about. I might have to skip some. But let me give you first a review of the principle I'm talking about, which is a very simple thing. Let's assume that we have a signal which is a sinusoid, has an amplitude A, has a frequency omega, and P is the phase. What we call as eternal model of the signal is the polynomial S squared plus omega squared, where S is the differential operator. In other words, when you operate, S takes the derivative, S squared takes the second derivative. Okay? So what happened here, we say that QS is the eternal model of this signal, because when we operate on D, see here, S squared plus omega squared operating on S, you get the first term here, then the S operates on A sine omega t, differentiates, gives S A omega cos something, you differentiate another time, it gives you this minus omega squared that cancels with the other term, it gives you 0. In other words, when this polynomial operates on the sinusoid, it rejects it, no matter what the amplitude is or the phase, as long as you know the frequency. Okay? So let's assume now that we have a system which has a transfer function, is y equal q over u, and we put as an input u a sine omega t plus p. So for people who know about body plots, this is how you get the body. You vary omega, and then you do a couple of plots. So when it operates on when G of S operates on that, what it gets as output at steady state is the magnitude of that transfer function, where S is replaced with J omega, and omega is the frequency of the signal. Then at the end you have A sine omega t plus psi, where psi is the phase shift, t plus the shift from G. So if G, however, had a numerator, S squared plus omega squared, right? Then Gj omega would have been equal to 0, because you plug here S equal to J omega, it's going to give you minus omega squared. So this will go to 0. So if G had a 0, add the frequency of the signal, then the output would have been, the system would have noticed, you will go, you get 0 at the end. Okay, so you put something which is sinusoid, and at the output you get 0. Okay, so the signal is just filtered out. But if G or GS has a numerator, has a denominator S plus square plus omega square, obviously Y will go to infinity. This is what we call the resonance. You know. Okay. So what we left from okay, go back. Okay, keep one. Now I go to one step further. I have a plan that is YGSU, and it has an output disturbance T, which is a sinusoid plus noise. Okay, and G is the ratio of two polynomials, Z and R. So, and I choose an input U that it has 1 over Q as a factor, where Q is the internal model of the sine omega t. Okay, so if I close the loop, I get this expression. I just plug U into here, I bring everything on the other side, and I get this expression here. Okay, so you can see from here, if the plant had the same factor as Q, these two will cancel, and Q wouldn't have any effect, right? Like it's not there. They give me this expression. So I rewrite this like this. You see the Q appears here. So if it's not canceled, it will appear here. It will operate on A sine omega t plus t. It will give a 0. And then the other term will be driven by noise. So the way this internal model works is that if you plug 1 over Q in the controller, the Q appears at the top and kills the disturbance. And this is a special case of the integral control, which most people know, like the PID and so on, where the QS is equal to S and appears as 1 over S in the control. Okay, so what we left from this is that the zeros of the plant should not have as a factor the internal model of the disturbance if we're going to kill it. But computationally, it should not be close. In other words, Z and Q should be strongly comprised. They should not be close to have a common factor. And the only information we need to know about the disturbance is the frequency. We don't care about the amplitude or the phase. As long as we know the frequency, we kill the vibration. And I gave you one configuration, but you can have a lot of different configurations where the Q, as long as the Q appears in front of the disturbance, to attenuate. The other thing we notice is that we kill the disturbance, the periodic term, but we did nothing to the noise. The noise is there, sitting driven by this transfer function. Let me go back here. You can see it here. So even though you choose a Q that kills the vibration, the noise is there and will appear in Y. The other thing we need to, I didn't mention, is that this transfer function has to be stable. Otherwise, the system will be unstable. So the Q you choose here to kill the sinusoid should be included in the analysis here for stability, but also for making this transfer function to have a low gain in the broadband spectrum of the noise. And the idea here is to make it less or equal to 1, because you cannot kill the noise. Okay? So but the thing you want to do is not to amplify it. Don't kill it, you cannot kill it, but you can easily amplify it if you don't do a proper design. So these ideas will go to the complicated case that I'm going to talk about. So the problem I'm going to talk about is that we have these vibrations and we don't know the frequency. Because if we know the frequency, there are plenty of tricks. And they're all based on this principle I mentioned, the internal model principle is called. So if the frequencies are unknown, the problem becomes very complicated. And here is, so that's a problem I'm going to talk about, and I'm going to go into the details now. And the way we deal with the adaptive case is that we assume that by somehow we first stabilize the plant. So we are dealing with only stable systems. So we design a controller that makes the closed loop system stable. So we have this configuration. Configuration is that you have a system with the transfer function, the output, the input, and the disturbance here that is divided into periodic disturbances and a term that represents the noise. And the disturbances are assigned, here is a sum of sinusoids, and here we have NF, NF sinusoids that we want to get. So this has a lot of applications. Every application that things moving and they're vibrating, that's where this theory would apply. So I put quite a few here from laser. The way I got into this area is because a company asked me to solve the problem of jitter in a laser beam device. And there are all kind of noise cancellation gadgets that they're in industry, on the plane, you can wear them. They're all based on this internal model principle, one way or another. Okay. So let's go to our problem. So our problem is to design some feedback here. We're just going to learn the frequencies, because remember, if we know the frequencies, we can kill them. So the idea here is to find some kind of parameterization to learn the frequencies and use the estimate of the frequencies in the internal model with a similar controller that I mentioned before to achieve the rejection of all the periodic terms without amplifying the broadband noise. Okay, so that's really the problem. So what we like to have is something like this. You can see the signal, the output here. It's all a mess, it has a lot of noise, it has a lot of these periodic disturbances all mixed up. And when we switch on the controller, we want to be left with just a low level noise. Okay, so you see this picture several times in the talk. So as I indicated before, there's a lot of work done in this area by different groups, calling it, every time they do something, they give it a different name, and it's becoming confusing. Repetitive control, do I have repetitive control there? Yeah, so from Suga's work, I don't think I could. But they give it a different name, but it all boils down to exact same thing. An internal model, how do you put it in the feedback, and how do you estimate the frequencies? Some people do state space, some others do input-output, some just do figure out the simulations that it works, so on, this lattice filter implementation. So when I look into this area, I saw a lot of inconsistencies, this method versus this method, but then they're all the same. How do you unite all these things? How do you put them together so it makes sense? So the common characteristic of this effort is that they use the internal model principle directly or indirectly. They abstract the controller structure. They have this QS that they find a way to estimate the frequencies. And the interesting thing from the estimation point of view is that if you model everything exactly, because you're dealing with periodic signals, you have what is called persistence of excitation. In other words, your output data contains all the information about the frequency, so the estimation becomes easy. You can easily estimate. The problem, though, that is missing from that puzzle is that if you do that, you don't have any flexibility to play to avoid amplification of the noise. So what happens in a lot of these methods, they reject the periodic disturbances and they amplify the noise. So the group of Landau had a competition before I didn't know because I just went into this area. And they got, he had an experimental facility. I will show the picture later on. So 8 groups participated. They sent their algorithm, they tested them, and Landau's algorithm became the #1. So it was better than anyone else. Okay. Then we published a paper in Mediterranean Conference in Crete, and his students saw our algorithm here. He went back, he put it on the system, and it beat their algorithm. So they called me, say, how did you do it? What did you do? And so on. And that's what I'm going to explain about. Then we wrote a few papers together, so on. And why our method was better? Because we make sure that the noise is not amplified. Nothing really. This is classical robust control idea. But with some, of course, in order to achieve that, we had to do over-parameterization. And when we over-parameterize, we lose the property that all these guys have. We lose the property of persistence of excitation, which guarantee exponential conversion. So that was the trade-off. And when you lose that property, then the stability problem becomes complicated to solve. So everybody, in order to prove something, they have to assume that everything is exact. And of course, they didn't bother about the noise, which is the main issue. I will show you samples here. So some of the problems was open is that the noise part, what if the zeros of the plant are not the same as the internal model, but they are close. So that brings the gain of the system very low, and it has problems with adaptation. Then we are talking about what if the plant parameters are also unknown or they have uncertainty. So we address all these problems in this body of work. So how does it work? When this 1 over Q of S is in the controller, what it does, it generates a sinusoid. So if you open the impulse function of 1 over S squared plus omega squared is sine omega t. So what happens when you have that term appearing in U becomes like an oscillator. It generates something, but is multiplied with some other things that we show, and it creates the anti-disturbance, a minus t here that cancels with the d. So on a higher level, this is the mechanism. Basically. So you have a U that becomes generates some oscillations that goes to the transfer function, and then boils down to create something which is like a minus t, and then it kills completely the disturbance. So the necessary sufficient conditions to be able to do that is that the plant would allow these frequencies to go through, okay? Which means the zeros of the plant do not have they should not be located at the frequencies of the disturbance. Otherwise, the sign will not go through to create this minus t. So eventually, our controller structure is like this. Okay. So here is the plant, the real system. There is a plant uncertainty here because we can never know the real system exactly. So we assume that G of 0, I put Q here, it could be discrete or continuous. So then we assume that we know the dominant part of the plant with the G of 0, the transfer function. So we use it here to generate signal, which we subtract from Y. So what you get here is the estimate of T. You do the calculations. What you get here is the estimate of T, assuming that the uncertainty is equal to 0. Because the uncertainty is not equal to 0, you get something more. Then it goes to this filter, which has this theta that we want to adapt to estimate, and a filter Q, which I show you how we use it, is to shape G of 0 in the frequency. So if you do that, the output of the plant can be expressed as 1 minus G of 0 minus G of 0 Fk times something inverse. So I'm using not just single input, single output, it could be for multivariable, driven by D. So the 1 plus delta m G of 0 F of K inverse is underneath, so it has to be stable for stability. The one on top, you can see here, is the one that will will make the effect of the disturbance 0. So we need to choose K. So F will shape G of 0, let's say in the frequency domain. K is the one, the transfer function that will be chosen to make this 0 at the frequencies of T. One way to do it is to use K equal the inverse of G of 0F. That will kill everything, right? But that cannot be done because that would require the use of differentiation and so on. The other thing, the approach we follow, we want K to be such that this transfer function here has a factor, the QS, the internal model of T. So if that had a factor of QS, that will, you can bring it here, and that will reject all the sinusoid terms, and you'll be left with noise. Okay. So here is the structure of these filters. Okay. So we, as I said before, we choose some more terrain, which is greater than twice the number of frequencies. And the first thing we want to, does this structure has a solution? In other words, will you be able to find this filter K as theta, which boils down, if we fix everything else, it boils down to this parameter theta, or the vector theta. And this theorem says that, yes, there exists a theta star for which all the periodic terms of the disturbance are completely rejected, if and only if the plant does not have any zero at the frequency of the disturbance. And n is greater or equal to twice the number of frequencies. But if n, if the order of this filter is equal to 2nf, then this theta star is unique. And this is what other people use. Make n to be equal to 2nf, so they have a unique theta star, which guarantees processor excitation. What is the problem with that? Is if we write down the system, right? Then for stability, you want this guy here with a multiplicative percentage to be less than 1. So this transfer function is always stable because the roots are the poles of the closed loop transfer function are the roots of this polynomial here, and the poles of this one, which are, because G of 0 is stable, K has stable poles, so this is stable. But this one may not be stable unless delta is small, and this is the condition that comes from the Nyquist criteria. And for the rejection of periodic disturbances, periodic terms, is that this term here has to be 0 at the frequency. In other words, it has the internal model as a factor. And of course, in discrete, the S being equal to J omega becomes the Z transform e to the J omega I PS. Okay. Now, the other thing we are doing here, in order to avoid amplification, we choose the theta star. Remember, if we over-parameterize, there are many theta stars. So among these many theta stars, why don't we choose one, the one that minimizes the sensitivity, the gain, and multiplies the noise? Okay. So if you do exact modeling, there will be only one theta star. So whatever you get as a sensitivity function for the noise is given. You cannot change it. But if you over-parameterize, then you have an infinite number of theta stars, and you choose the one that minimizes this noise. Okay? It means it brings a gain of the function that multiplies the noise less or equal to 1. So here is an example of, just to get an idea, is first of the system. We model it, I believe, we model it first of the system. There is one frequency and noise, which noise is Gaussian, amplitude less than 0.1. So if this term here has a pair of complex zeros at the same frequencies, then the periodic terms will be completely rejected, as we talked before. And here is the problem that I mentioned before with the noise. So if you don't understand the map, you will understand this picture. So this is the output of the system without any control. Okay, you can see here the frequency, periodic frequency, and the noise effect all mixed up. At t equals 20 seconds, we switch this adaptive control. And we switch it when the order is equal to 7, still over parameter, but it's not, doesn't have a lot of flexibility. You see, the periodic terms are all eliminated, but the noise is amplified. In fact, the output of the system is worse than it was before the control. So it's totally useless. If we make n equal 15, we get a better picture. If we make it n 30, we get what we like to have. No noise amplification at all. Okay? You have to keep in mind that feedback cannot do anything to noise because it's a broadband noise. Bandwidth of the controller is narrow band, so it doesn't get into the high frequency region. So the only thing in control you are trying to do is not to amplify. And you can see here that if we don't pay attention, we can amplify it and make it, and that defeats the purpose of the whole approach. So here how it works when n is equal. This is the sensitivity transfer function. you can see here at the frequency of 25 how the gain went down considerably, right? This is the gain of this function here, right? It's almost zero at the frequency of the disturbance. And away from that, you can see if n is equal to 7, you can see this is greater than 0 in the logarithmic scale, which means it's greater than 1. And this is what we see. But for n is equal to 30, this sensitivity function, which is this one here, is very less or equal to approximately 1. And that's why, so what you saw in the time domain, I show it to you in the frequency domain too. So the way we estimate these parameters of the internal model, we get all these parameterizations. There are some like least squares type of recursive algorithm to estimate the parameters of basically it's estimating all these theta star terms that were in the feedback loop. And we ended up with something that is like an adaptive filter, right? And that's but you work it out. Theory says everything will work out, but the theory doesn't tell you, when you go into practice, something that is greater than 0 makes a lot of difference, right? Theory says greater than 0, you're fine. But greater than 0, 10 to the minus 10 is greater than 0. But computational, this is probably equal to 0, right? So we have to look at this from the practicality point of view. So if the gain, if the Planck has a small gain at the frequency range of interest, that means all the signals will be scaled down. And if you are relying on the signals to drive your learning process, then it's not going to be a lot of energy. So the gain cannot be low. Again, theory doesn't tell you that. If you put too much large gain, then you push the bandwidth of the controller and then you excite their model dynamics. You have problems with stability. So you have to have something, and in robust control is called loop shaping, and people know that very well. It has to be something that give you a high gain in the low frequency range, and it drops down rapidly in the high frequency gain where you have noise and a model dynamic. So here, what you do in this case, you design this filter f of s that I put here. So G of 0 in f of s is such that everything is inside this cube, let's say. So it has a high gain in the frequency range of the disturbance, and it drops off to 0 in the high frequency. So it's a combination of ideas from robust control and adaptive control. If you are a control engineer and you go to industry, 98% of the problems is about this stuff, not the adaptive stuff, but this loop shaping and the bandwidth and things like that. So this stuff are classical and it may not be interesting from the research point of view, but they're extremely useful in the control of real systems. So if we put this, what we designed together, then we achieve the result, but because of adaptation and so on, the lack of persistent excitation in this case, we get that the mean square output depends on the size of their model dynamics and the size of the noise. That's what we get. The periodic disturbances are gone. They are totally rejected. Okay. And if there are no model dynamics and no noise, then you get the exact convergence of the output to 0. So because you can't get rid of the noise, so at the end your output will be moving a little bit with the noise. Okay? But if in an ideal situation you remove the noise, then you go down to exact result of y going to 0. So the same thing we can do in the continuous time case. We did in discrete, continuous, multivariable, so on, the same tools. So we try to, with this work, we try to unify, because something you see in adaptive, someone does something in continuous. Then another group does the same thing in discrete. And it appears that the two are different, but they're not different, because they use different symbols, different things. People don't look at it carefully. And they think it's a different thing. But so one thing we try to do is to make sure that all these things are unified, really. So there's no point to talking about, because the young people who come into the area, they get confused. One is discrete, dealing with discrete time system, and the other person is continuous person. So when with a simple Euler approximation formula, you go from one to another very easy. So the same result here. And here is the sum of the simulations. You can see here the importance of the filter F. You can see this is without, when F is equal to 1, that's the gain of the plant, right? Very low gain here. Remember, this is the logarithmic scale, so minus 20, close to 0. And with F, we reshape it to have this gain, much higher gain, and follow at the high frequency gain. And that's in the frequency domain. Now, in the time domain, when you run, here is you have the open loop system with the noise and the periodic disturbances. You switch on the controller, the adaptive controller, without shaping the plant transfer function, so the filter is 1. You get nothing, and no attenuation. Okay? Because the system doesn't converge fast because the gain of the system is very low. And here what happens when I reshape the plant transfer function with the filter F, you get what you expect. All the periodic disturbances are completely removed. And what you get at steady state is the level of the noise. And here is something that the frequency now are changed, because the whole idea is of this, the motivation of the case of unknown frequencies was the frequency may change, because if the frequency is fixed, you run an FFT at the output, you get the frequencies, and you have your Q, you don't need adaptation. Okay? But the frequencies may change. So we'll be working on this change in frequencies in this case. And you can see from here, the frequency changes from 70 and it goes linearly to 100. And you can see the result here. So you can see here that we have a little bit of a problem, because here we assume in our analysis and design that omega is kind of fixed. So, but fixed, it can be fixed over an interval of time and then change again. But in this region here, it's not piecewise constant, changes with time. So it seems here that this structure of controller is having a little bit of problem. It's giving you higher steady state error run. So the rejection is not as complete, and we will address that. We address that in a current paper. So, and this is the case where we are considering, motivated from this problem, that the frequencies now are time varying. So you have this AI of t, and the derivative of A of t is omega t. So AI of t is the integral of some function omega I. And if omega I is, if AI dot is equal to constant, then this becomes omega t, and you plug it here. Okay. Now the eternal model here in this case, that this polynomial I was talking about, that operates on sine and rejects it, it becomes a polynomial, differential polynomial operator, but the coefficients are time varying. Coefficients depend on the omega and derivative. So it's a little bit more complicated case. We just wrote the paper, sent it for publication. But we found that in this case, we can develop the eternal model, which just has these coefficients are time varying. Back here. Yeah, okay. So here is the same structure. We have to, because this theta now is time varying, we have to and the coefficients of the internal model are time varying. So we have to watch out for commutability because the constant you can bring it in front of the differential operator or behind. But if it's time varying, if you put it in the front, then it gets differentiated. So it gets mixed up. So how you parameterize the system, it becomes very important. So here we have the same result, except for one difference. We still need this comprimeness. We don't want the zeros of the plan to have any of the roots of the internal model. And we can reject the disturbances, the periodic disturbance, but not exactly, unless the plan is minimum phase. If the plan is minimum phase, then the rejection of these time varying disturbances becomes exact. And that was an interesting result because we don't have this problem in the case where the disturbances have fixed frequencies. So this minimum phase is for people who may not be familiar with this minimum phase, that means the zeros of the plan are stable, okay? Within the unit circle or the left side of the S-plane. So here is the demonstration of that, which you have one frequency like this. And this is a plan which is very similar to this, except that it has an unstable zero. That's equals 100. Okay? You can see from here that the disturbance is completely rejected. And here has this a steady state, something like this. It's small, it's attenuated, but it's not zero. And that's what we predicted from analysis. So the idea here, how to deal with this minimum phase assumption. So this is the control in this time varying case. And we repeated the example that I gave you before from going with this -3t term. And you can see here that we got a much better result than before. And here is another example, the exact same example. Remember that in the middle here was a big, when you are at this region from 20 to 30, here the amplitude was very high, a little bit much higher than the other. You can see in the time varying case, because we changed the algorithm to account for time variations, we are able to show this not to be affected by the change of the disturbance at all, of the frequency at all. So then we can extend this to the multivariable case, where now we have to deal, we're talking about the zeros of the plan. Now we're talking about the transmission zeros. Okay? The zero of the plan is the value of S that makes the output equal to zero, right? When you go to the multivariable case, you have a matrix now, right? So what do you mean that, well, you can make all the elements equal to zero, and that would be a zero, but here the zeros become the rank of the matrix. So you can have cases where you get zero output in certain directions for some choices of F. So that's, roughly speaking, what the transmission zero, but everything that you had in the single input, single output case, it extends to the multivariable case. And again, all the parameterizations, the formulations just become vectors instead of scalars. And again, the parameterization is now, instead of z, let's say here being a scalar, it's a vector, and so on. So nothing, matrix theory, nothing different from the single input, single output. And again, the estimation scheme and the results now of similar nature. There's no term here that depends on the disturbance, just the noise, the level of the noise, and the uncertainty in the model dynamics. So this is one of examples. Probably examples are more easy to see. We have two channels which they have different frequencies, right? And these are periodic disturbance terms that you don't know. They are there, they're periodic, but you don't know them, and they could change with time. And at 25 seconds, they even change frequencies. They become something else. And you can see here the shaping of the, how to shape here the singular values is equivalent to the case of single input, single output. And here is the case where we don't do anything with the filter. So theoretically, it should work, right? But taking into account practical considerations, no, because the gain of the transfer function is very low in this case. So as you can see here, we switch the input at 10 equal at t equal 10 seconds, not much improvement. Okay, and as the frequency change, you know, this is it doesn't compare well with the without control, which is the first 10 seconds. And here what happens with some filter. Okay, reshaping, the algorithm is the same, just reshape the plan transfer method. And here when we increase the filter, we do more over parameterization, we improve performance even better. Now we do something crazy, we don't know the frequencies, how many they are. So we do these shift disturbances that have many frequencies. Okay, so they're all concentrated in this region here, right? And we want to see how the controller does. And you can see from here that, as I said, we switch it on at 10 seconds. So what you see before the 10 seconds is what the system does without control. When we switch the controller, you see we eliminate all these disturbances, even though they are very close together now. So this is the system that Landau has, which is a mechanical system that creates an oscillating shaft, and they apply the control. So this is a real system in the lab, in the shaker. And I haven't seen it, but so picture. So we used to send algorithms there to test them on this system and confirm whether we get a simulation. So apparently they have some flexibility to change, make it from single input to multivariable, to put time vary frequencies, and so on. So, and then we remember we talk about this unknown plan. So one thing that everybody assumes is that the plan model, which is the G of 0, is known exactly. So we decided, okay, what if we don't know that plans are survived? So if we obtain a result that for the case of G of 0 being minimum phase, G of 0 has stable zeros, then we can solve the problem of estimating the unknown plan, as well as rejecting the unknown harmonic. There are no harmonics, or there are no sinusoid surfaces. And this has two levels of estimation. One that involves the estimation of the internal model of the disturbance, and another one, the estimation of the plan parameters. Then it goes through the control law, and it becomes like similar to what we have in model reference adaptive control. So again, I don't want to get into all these details, but the assumption, the main assumption here, which actually restricted, is that the zeros of the plan are stable. And we get a similar result here, that the mean square error is of the order of the uncertainty and the noise. And here is some of the results that we apply to an unknown plan. As you switch the controller at 10, and we estimate the plan and the disturbances, and even when the The stepwise characteristics are changing. This is the control input, and this is the estimation of the parameter. That's, you can see the start from initial condition and convert to something, so on. So the two work together. Here is another case. And what happens here, we switch abruptly to a completely different frequency. So you can see the jump here, generates signals, so it can estimate, but the system catches up pretty fast. So the open problems in this area is that if we have now unknown plants which are not necessarily minimum phase, and they're also time varying, how do you do it? Apparently, the problem in that case becomes a parameterization problem, which Mario knows very well. The parameters cannot be expressed linearly in a parametric model, so we cannot have a good estimation algorithm. And in this case, becomes similar to the problem of direct and indirect adaptive control, where you're trying to avoid this problem of stabilizability, which has to do with the estimated plant being controllable and observable at each time t. So the conclusion of this work is that the first thing that I really learned and appreciate, and students who work on this for a company in aerospace, and he's doing extremely well because he learned that stuff so well, this loop shape and the interaction with adaptation, and that's what they really need in industry. And most of our students don't know that because we get excited with research topics and teach them nonlinear and this and that, and very little attention is put into the fundamentals, which you can theoretically prove things, but if you don't think practical and so on, then what you develop, it may not work, and you may not know why. That's the worst scenario. So we combine this engineering intuition, the advanced theory and stability, and some basic common sense which comes from this loop shaping and robust control. Create a system that is practical, and yet it guarantees all the analytical conditions for stability and robustness, and it's being implemented on a real system. Actually, it's implemented by also the Air Force on a platform with laser beams, and we don't know what they got because it's became all confidential after they got the algorithm. So as I mentioned before, we use also filtering in addition to the adaptive control techniques to reject these vibrations that has a wide range of applications. We put one of these, I work on a disk drive control, where you're trying to control the beam that reads the hard disk to stay within the track with an accuracy of 0.1 microns, an extremely high fidelity system. And we use an idea like this. A little bit, we knew the frequencies there, so it was not a reason to use adaptive, but we were able to stabilize it with that accuracy, 0.1 micron. And we put it on a WD, on a Western Digital disk drive. So it was just to show you how many applications this rejection of vibrations or noise amplification has. Every disk drive on the computer has something that is based on this principle I presented here, because the disk rotates very fast, right? But there are harmonics. It doesn't go exactly at the center. It goes a little bit off. And with these principles, you make the head moving also at the same way. So the relative position is always the same. It's always zero. Okay. So it has a lot of different applications. Of course, the use of the adaptation here adds a lot of computations, and you cannot put it on the disk drive because very up there, 1 cent. Anything you put that brings the price 1 cent is a bad thing, because the profit margins are extremely low in those. That's where you get cheap computers. So am I going backwards now or forward? Okay. So with this, I'd like to stop here and thank you very much for your attention. I don't expect you to follow all the equations I have, but I hope I convince you that there is a way to get rid of sinusoids if they appear at the end of any system. There are techniques to do it, and this is one of the techniques. Thank you.
Maybe we can start with questions from here, and then we go to the audience online. Any questions, comments?
I understand. Well, I mean, it sounds like the more you overparameterize, the better. But I cannot intuitively, it doesn't seem right to me. I mean, after a certain point, you may.
Well, after a certain point, you don't get any benefit.
One of the simulation results, when you were changing the frequency abruptly,
Yeah,
was showing that it had for a short time period a spike, a huge.
yeah. So what happened in that case is because, whenever all the signals are very low, right? All the signals are very low. So, and most of the thing the signal has is noise. So the noise to signal ratio, the signal to noise ratio is very, very low, because you already convert, right? Now you disturb the system. You put something that the information is not on that region. So what the adaptive does, creates this transient, shakes the system a little bit, right? Now the information becomes in the data, in the output, and it learns what to do. So it's a natural phenomenon.
I was just wondering whether in that time period, the more you overparameterize,
No, the overparameterization has more to do with the noise. And you can keep increasing that the order, but after a certain point, you go to the level of the noise, you cannot go beyond that. So in this case, in the example I showed, you go above, the highest I showed you was 30. You go 50 or 40, 35, you don't get any improvement, because you are already within the level of the noise. There's no way to reduce the effect of noise. Okay? No method can eliminate noise. Even, because it's very intuitive, like violating a law of physics. So whenever you have a change in something, when the system is converged already, and now something else happens in the system, then the system will generate a transient, so they gets gets excited. So the information becomes in the data, so you can learn. You have all these signal processing algorithms and so on, and everybody talks about data. I have a lot of data, transportation. Everybody, every office you go, he said, I have 1 trillion of data. It must be useful. But it's not the amount of data you have. It's what information the data has, right? You measure all the speeds of the cars, and they are all at 50 miles per hour, and you measure it every second, they're all 50. I only need one, right? One will disappear. What am I going to do with 1 trillion data? So the idea is to have the data, to have the information. So you can have all kind of algorithms. If the data are not if the information is not in the data, you will never get it. And some of these results, as you notice, say why you get a transient here, so on. It must be something wrong, but the action is very intuitive. It should behave this way. Otherwise, it doesn't make sense. Most likely, if you get a different result, most likely something wrong with your code. Any other questions? Yes, Thomas.
Well, Petros, enjoyed your presentation very much.
Thank you.
reminds me some of this old classical. So, this loop shape, you have a very good point. These are the.
Of course, you spend time with a giant in this Zen, right?
For Zen. So I was wondering, your formulation, the first problem was sensitivity minimization.
Right.
Yes. Based on with noise sinus. Sinus.
No. The noise is broadband.
So you mean you put? I saw in some of your models, your disturbance, you put time.
It's a sinusoid plus noise.
The other one, you had this, I think, call it V.
Yeah, that's a noise, right?
That V now, is it the support of the noise?
If it's a broadband noise, it could
So
be a
it's
sine, it could be Gaussian, it could be usually Gaussian, or so on. It's a broadband noise.
So if it's Gaussian, your result, if let's say it's IID Gaussian, how are they affected if you increase the variance of the noise?
Yeah, that's the thing. We are not okay. We are not getting into the stochastic part. So you can also get this V as Gaussian noise with some statistics, covariance and so on, and do stochastic control. Yeah, what we are not doing. What we assume about V is some broadband disturbance which is bounded from above. That's all. It has an upper.
It's no Y.
Yes.
It's no Y.
It's no Y.
If it's Y, no Gaussian Y.
No, it's not Gaussian Y.
It is not a finite support.
Right. There's no way. It doesn't have to have zero mean or anything. Just the best way to describe it is a broadband bounded disturbance. That's more accurate than calling it noise. Because when you say noise, then you get into what kind of noise, and
that's right.
Then you get into the stochastic control idea.
So the other problem also you talk about is when you do also try to understand when you start sensitivity minimization and plan uncertainty. It was a joint formulation or a separate formulation?
Okay, so in the equation I had was the sensitivity factor was 1 minus something, some transfer function operating on the noise. Okay. So what you want to do, you want to get this minus term, make it as small as possible.
Yeah, I was wondering whether you address the simultaneous.
Yeah, but you do it offline. You do this offline. You don't need to do simultaneous. You do it offline. Of course, when you go into the adaptive, we don't do that because everything is time variant. Okay, what you do every time t, it's not feasible. So we show in the non-parameter case that this helps, and then we let the adaptive find. That's the idea, but we have no proof in the adaptive case that it will find, because everything is a mess. It just becomes a nonlinear system. But you use the intuition of existence in the non-parameter case, how it works, and so on, and you expect the adaptive for some reason to be able to find it. And what we see simulations, it does a good job. That's fine. Okay, so there is a little bit of
very nice. Thank you.
missing link there.
Are there any questions here, or shall we go?
Can we use your approach in real time?
Of course. I mean, we develop it to be used for real time. No, but certain, I mean, if you want to choose there are certain things that if you know the plant transfer factor, you want to design a controller around it, right? That's offline. You can do it offline. The filters, I mean, a lot of things are done offline. So it depends what you are doing, but the adaptive the algorithm that moves and estimates and so on is real time.
Just to understand the math, but have you tried to compare your method with machine learning?
This is machine learning. Okay. It's a class of machine learning. Machine learning is, I have the students who come to me and say, I want to do machine learning. I don't like that. Well, you are doing machine learning. When machine learning, the parameter estimation in machine learning. So there are a lot of, it's a name that covers a very broad area. Neural networks also can be viewed as machine learning. Right? So it's a lot of, it's a name every now and then. 10 years ago it was called intelligent systems. Now it's machine learning. Machine learning is it's a wide class of different methods, from regression analysis, from statistical analysis, from going into parameter estimation, so on, dealing with data. And so it covers all these different methods. Most of them are very classical. Nothing new there, just need to know how to do it. And there are a lot of software tools. And then you get into the neurals, lines, and adaptive, so on. But, so the difference here is that what we are trying to do is control, because we are dealing with safety and stability, which has implications for safety. We like to prove whatever we do. Not like you take a big neural network, plug it here, you get an image, you compare it with some other. Safety doesn't come there. If it converges, fine. If it doesn't, nobody gets hurt. But when you do control design, you can, the plane may explode. So, things have to be, stability becomes very important. So you have to make sure you have analytical guarantees and so on. And here you're closing the loop, you're affecting stability. Imagine if you put something like that on a plane, on an aircraft, you can bring the aircraft down. If you make a mistake, you're not within the stability margins. And in the aircraft, they pay a lot of attention to the stability margins. So you can't put a neural network driving guiding a vehicle, not to pilot on a plane. You never have a neural network. It has to have some of these fundamental, robust control ideas, and maybe adaptive, but under a lot of close supervision. There were people who tried to put neural and all these things. People who fly them, you fly, you get on the plane. And when you say that, everybody backs off. So so there is in this umbrella of machine learning, there are methods that are offline, process data, you extract information, you make correlations. There's the dynamical part also, that things are moving, which is more complicated. And now, apart from control, using those dynamical methods, is we have to show stability. We have to be concerned with stability and robustness also, because of the nature of the application.
Do we have any questions from the audience? I think we have like more than 50 people listening. I don't know. Are there any?
One question.
One question.
So, Paralabos Rosidis is asking, if we go back to slide 5, you said that the trick produces a signal that is driven by noise. Could the signal be used as estimator of the noise signal and fed back to the expressive?
This guy understood. This time, 5 now. Number
Petros, we have to leave it. There's another.
Yeah,
group
okay. Shall I answer them?
Yeah.
Number 5. Okay, what was the question?
You said that the trick produces a signal that is driven by noise. Could the signal be used as an estimator of the noise signal and fed back to expressive?
Yeah, okay, that's a good question. You cannot estimate the noise. Okay, the noise, assuming this, there is randomness. What is that estimate? But you could estimate the frequency here. You can have a parameter estimator to estimate, not to estimate, no, I'm sorry, you cannot estimate omega. To estimate the amplitude and the phase. There is a way to do it. You want to estimate A and T from that configuration, yes, but not the noise. The noise is assuming stochastic, assuming it's something that changes, maybe not exactly white noise, but something that it can roll, it doesn't repeat itself. It has no pattern, it changes very fast, so on, small amplitude, but fast frequencies. A lot of frequencies together, but with a very low amplitude, which makes it difficult to take them out, for example, and high frequency too.
Okay. But we need to leave the room because there's another reservation in 5 minutes. So I would like to thank the speaker. I think it was a very, very useful presentation on some of the practical aspects of using feedback control in real systems, and also some very nice theory regarding estimation, noise disturbance, things like that. So thank you very much, Petro, and thank you for attending the presentation.
Amen.